Hi everyone, welcome back to my channel Civil Eng Notes. In today's video we are going to talk about isoparametric quadrilateral elements and how their shape functions work from 4 node elements all the way up to 9 node elements. Shape functions are the backbone of finite element analysis, so understanding them clearly will make the rest of FEM much easier. Okay, let's start with the 4 node element, the simplest quadrilateral element. On the left, we have the physical element in Cartesian coordinates. It can be skewed or irregular, but the key point is that the nodes are always numbered in a counterclockwise direction. So 1, 2, 3, and 4, counterclockwise direction. On the right, the same element is shown in natural coordinates using R and S. Here it's always drawn as a perfect square, a 2 by 2 element ranging from -1 to +1 in both directions. So the coordinate here would be -1 and -1, and here it is +1 and +1. Here it would be +1, -1, and here it is -1, +1, and the middle is 0 and 0. The dashed red lines show the constant values of R and S. For example, R equals to -1 corresponds to the left edge, and S equal to +1 corresponds to the top edge. This mapping makes it much easier to define the shape functions, which we will use to describe the displacement field inside the element. Now let's see how we can actually find the shape functions. There are two simple rules to remember. Rule number 1. The shape function for a node must be equal to 1 or unity when we are exactly at the node's position in natural coordinates. Rule number 2. The same shape function must be 0 at all other nodes. Let's apply these rules to find the shape functions for node 1 here. Look at the square on the right. Node 1 is at bottom left corner with coordinates r equal to -1 and s equal to -1. To satisfy the second rule, the shape function for node 1, which we call it n1, must go to 0 at nodes 2, 3, and 4. So if we include the factor 1 minus r, or r equal to +1 in n1, it will automatically become 0 at nodes 2 and 3 because at those points r is equal to +1. And if we include the factor 1 minus s, or s equal to +1, then n1 will also become 0 at node 4 because this line is s +1. So putting all these together, we can write n1 as this equation. It includes 1 minus r and 1 minus s, and we have a coefficient a. Here a is just a constant that we'll adjust later to make sure rule number 1 is satisfied, meaning n1 equals to 1 at node 1. Now let's apply the first rule to finalize the shape functions for node 1. We already wrote that n1 equals to a times 1 minus r times 1 minus s. At node 1, r is -1 and s is -1. According to rule number 1, the shape function must be equal to 1 at this node. So let's plug these values in this equation. R equal to -1 and s equal to -1. So we will have 1 minus -1, so which will be 2. Again 1 minus -1, this one also will be 2. And according to the first rule, n1 should be 1 at node 1. So that gives us a equal to 1 over 4. So finally the shape function for node 1 becomes 1 over 4 times 1 minus r times 1 minus s. This satisfies both rules. It equals to 1 at node 1, and it automatically goes to 0 at all other nodes. Now that we have derived n1, we can follow the exact same process to find the shape functions for the other nodes. For node 2, r is plus 1 and s is minus 1. So the function comes out as 1 over 4 times 1 plus r times 1 minus s. For node 3, r is plus 1 and s is also plus 1. So n3 would be 1 over 4 times 1 plus r times 1 plus s. And for node 4, r is minus 1 and s is plus 1. So n4 becomes 1 over 4 times 1 minus r times 1 plus s. So together these four functions form the complete set of shape functions for the bilinear quadrilateral element. Each one is equal to 1 at its own node and 0 at all other nodes, perfectly satisfying the two rules we started with. Now let's move on to the 5-node element. Compared to the 4-node element, here we have simply added one extra node between nodes 1 and 2, right in the middle of the bottom edge. On the left, you can see the physical element in Cartesian coordinates. Again, it can be distorted, but the node numbering still goes counterclockwise. Notice that node 5 lies on the edge between nodes 1 and node 2. On the right, in natural coordinates, the mapping makes things much clearer. The element is still a perfect square, but now we see an extra point, node 5, located exactly at r equal to 0 and s equal to minus 1. This is how higher order elements are built, by adding more nodes along the edges or even inside the element to capture more accurate variations of the displacement field. Now here is the tricky part with the 5-node element. Node 5 actually creates a problem. Why? Because at node 5's location, which is r equal to 0 and s equal to minus 1, shape functions n3 and n4 are already 0, because 1 plus s would be 0 at s equal to minus 1. However, nodes shape functions n1 and n2 are not 0. So if you plug node 5 coordinates in n1 and n2, these shape functions would not be 0 anymore. So this means that the interpolation doesn't correctly account for node 5. Even more importantly, the bottom side here now has 3 nodes instead of 2. So this means that this side can no longer be represented by a straight line. The interpolation is no longer purely linear. So what do we need to do now? We have to modify the shape functions n1 and n2, and also we need to define a brand new shape function for n5. This adjustment ensures that node 5 is properly included in the interpolation, while still satisfying the two main rules for shape functions. Now let's carefully build the shape functions for node 5. Remember the two rules. It must be 0 at all other nodes and 1 at its own node. So first, let's make sure it's 0 at nodes 1, 2, 3, and 4. If we include the term 1 minus r, it automatically goes to 0 at nodes 2 and 3, because at nodes 2 and 3, r is equal to plus 1. And if we include the term 1 plus r, it goes to 0 at nodes 1 and 4, because r is equal to minus 1 at these nodes. Multiplying those together gives us 1 minus r times 1 plus r, which is 1 minus r squared. This takes care of all 4 corner nodes. Next, we need a term involving s. The lowest order choice is 1 minus s. That way, at the top edge, where s is equal to 1, the function becomes 0, which is exactly what we want. So a good candidate for n5 would be a times 1 minus r squared times 1 minus s. Finally, let's apply the first rule. At node 5, we must have n5 equal to 1. Node 5 is at r equal to 0 and s equal to minus 1. Substituting those values gives us 1 should be equal to a times 1 minus 0 squared, which would be 1, and 1 minus 1, which would be 2. So this gives a equals to 1 over 2. So the final expression for node 5 shape function is n5 equals to 1 over 2 times 1 minus r squared times 1 minus s. This satisfies both rules. It equals 1 at node 5 and 0 at all other nodes. Now that we have defined n5, we also need to adjust the functions for nodes 1 and 2. Let's see why. At nodes 5 location, r equal to 0 and s equal to minus 1. If we use the old formulas for n1 and n2, we don't get 0. In fact, each of them gives us 1 over 2. That means at node 5, the displacement would still be influenced by nodes 1 and 2, which violates the shape function's rule. But at the same time, we know that at node 5, n5 must be equal to 1. So here is the fix. We subtract a fraction of n5 from both n1 and n2. Specifically, since both of them were giving 1/2 at node 5, we can subtract 1 over 2 n5 from n1 and n2. That way, at node 5, both n1 and n2 go to 0, and only n5 remains equal to 1, exactly as required. So the modified shape functions become these values. n1 would be 1 over 4 times 1 minus r times 1 minus s minus 1 over 2 times n5, and n2 would be 1 over 4 times 1 plus r times 1 minus s minus 1 over 2 times n5. This adjustment ensures that the interpolation works correctly along the bottom edge, now that we have 3 nodes instead of 2. Alright, now we have the complete set of shape functions for the 5-node quadrilateral element. For node 1, you can see that we have subtracted half of n5, the same for node 2 or n2. n3 and n4 are the same and they have not changed, and n5 is 1 over 2 times 1 minus r squared times 1 minus s. So again, notice how n1 and n2 had to be modified to subtract out half of n5, while n3 and n4 stayed exactly the same. Together, these shape functions satisfy the two rules. Each one is equal to 1 at its own node and 0 at all the other nodes. So now the interpolation along the bottom edge here is quadratic instead of linear, exactly what we want when we add an extra node. Next, let's look at the 6-node quadrilateral element. This time we add a new node between nodes 2 and 3, right at the midpoint of the right edge. On the left, you see the physical element in the Cartesian coordinates. Again, it can be irregular, but the numbering always goes counterclockwise, with node 6 sitting between nodes 2 and 3 here. On the right, in natural coordinates, the situation is much clearer. The element is still mapped as a perfect square, and node 6 appears exactly at r equal to +1 and s equal to 0. Just like in the 5-node case, adding this extra node makes the interpolation along that edge quadratic instead of linear. This gives the element more flexibility to represent the displacement field, which means higher accuracy in the finite element analysis. Now let's find the shape function for node 6. First, remember the two rules. It must be 0 at all the other nodes, and it must be 1 at its own node. Node 6 is located at r equal to 1 and s equal to 0. So to satisfy the second rule, n6 has to vanish at nodes 1, 2, 3, 4, and 5. To make that happen, we choose factors that automatically go to 0 at those nodes. Along r direction here, since node 6 lies on the right edge where r is equal to 1, the function must include 1 plus r. That way it becomes 0 at the opposite edge where r is equal to minus 1. Along the s direction, the function should be quadratic because now the right edge has 3 nodes. So we include both 1 minus s and 1 plus s, which combines and gives us 1 minus s squared. So a good candidate for n6 would be a times 1 plus r times 1 minus s squared. Now apply the first rule. At node 6 itself, when r is equal to 1 and s equal to 0, substituting these values gives us 1 should be equal to a times 1 plus 1, which is 2, and 1 minus 0, which is 1. So that gives a equal to 1 over 2. So this means that the final shape function for n6 is 1 over 2 times 1 plus r times 1 minus s squared. This satisfies both rules. It's 1 at node 6 and 0 at all the other nodes. Now that we have defined n6, we need to adjust the shape functions for nodes 2 and 3. Here is the issue. At node 6, if we look at the old formulas for n2 and n3, both of them will give us 1/2 instead of 0. That means node 6 would still be influenced by nodes 2 and 3, which is not allowed. But remember, at node 6, n6 is equal to 0, and all the other shape functions must go to 0. So just like we did in the 5-node case, the fix is to subtract a portion of n6. Since both n2 and n3 were equal to 1/2 at node 6, we subtract half of n6 from each of them. That gives us the corrected n2 and n3 shape functions. Now at node 6, both n2 and n3 correctly go to 0, and only n6 is equal to 1. This way, the interpolation along the right edge, which now has 3 nodes, becomes quadratic. Here we have the full set of shape functions for the 6-node quadrilateral element. For node 1, you can see how n5, half of n5 is subtracted. For n2, half of n5 and half of n6 are subtracted. And for node 3, half of n6 is subtracted. And node 4 is not changed. And we have n5 and n6 as we found before. Notice how nodes 1 through 4 started from the bilinear functions, but nodes 1, 2, and 3 had to be modified when we introduced extra nodes along their edges. With 6 nodes, 2 edges, the bottom and the right edges, now have quadratic interpolation, while the other 2 edges remain linear. This extra flexibility makes the element more accurate than the basic 4-node version. Next, let's look at the 7-node quadrilateral element. This time we add another node between nodes 3 and 4, which is the midpoint of the top edge. On the left, you can see the physical element in Cartesian coordinates, and on the right, the same element mapped into natural coordinates. Notice that the node 7 lies exactly at r equal to 0 and s equal to plus 1. So now along the top edge we have 3 nodes instead of 2. That means the interpolation there is no longer linear. It becomes quadratic, just like we saw for the bottom and right edges in the 5 and 6 node cases. The key idea is that with every new mid-side node we add, one more edge of the quadrilateral is upgraded from linear to quadratic interpolation, giving the element more flexibility and accuracy in representing displacement fields. Now let's find the shape function for node 7. Node 7 is located at r equal to 0 and s equal to +1. So to satisfy the second rule, n7 must go to 0 at all the other nodes 1, 2, 3, 4, 5, and 6. To make that happen, the function should be quadratic along the r direction and linear along the s direction. So we start with the factors 1 plus r and 1 minus r, which together gives us 1 minus r squared. This ensures that n7 vanishes at the left and right corners. Then to take care of the vertical direction, we multiply by 1 plus s. This ensures the function goes to 0 at the bottom edge, where s is equal to -1. So our candidate for n7 would be a times 1 minus r squared times 1 plus s. Next, apply the first rule. At node 7, where r is 0 and s is equal to 1, the function must equal to 1. So r is 0 and s is equal to 1. So if you satisfy this equation, the coefficient a would be 1 over 2. That gives us the final expression for n7, which is 1 over 2 times 1 minus r squared times 1 plus s. And that's the shape function for the new mid-side node on the top edge. Now let's see how the introduction of node 7 affects the other shape functions. At node 7's location, which is r equal to 0 and s equal to 1, if we use the old formulas, both n3 and n4 give a value of 1/2 instead of 0. That means node 7 would still be influenced by nodes 3 and 4, which is not allowed. But remember, at node 7 only n7 should be equal to 1 and all the other shape functions must be 0. So just like before, we fix this by subtracting half of n7 from both n3 and n4. That gives us the corrected forms, as you can see here. Now at node 7, both n3 and n4 correctly go to 0 while n7 equals to 1. This way, the interpolation along the top edge becomes quadratic, exactly as intended when we added the mid-side node. Here is the complete set of shape functions for the 7-node quadrilateral element. You can see how n7, half of n7, is subtracted from n3 and n4. The important point is that now 3 of the edges, the bottom, the right, and the top, all have quadratic interpolation, while the left edge is still linear. So each time we add a mid-side node, one more edge becomes quadratic, and the element gains more flexibility and accuracy. Now we move on to the 8-node quadrilateral element. This time we add one more node between nodes 4 and 1, right at the midpoint of the left edge. On the left, you see the physical element in Cartesian coordinates, and on the right, the mapped version in natural coordinates. Node 8 lies exactly at r equal to -1 and s equal to 0. With this, every edge of the quadrilateral now has 3 nodes: the bottom, right, top, and left sides. That means all 4 edges have quadratic interpolation. So the 8-node element is the complete second-order isoparametric quadrilateral, where every side is represented by a quadratic curve. This gives a much more accurate interpolation compared to the lower order cases. Now let's find the shape functions for node 8. Node 8 is located at r equal -1 and s equal to 0. So to satisfy the second rule, n8 must vanish at all the other nodes, 1 through 7. Along the R direction, since node 8 lies on the left edge where R is equal to -1, the function should include the factor 1 minus R. This makes sure it goes to 0 on the opposite edge where R is equal to +1. Along the S direction, the edge has 3 nodes, 4, 8, and 1. So the function must be quadratic. That means we include both 1 minus s and 1 plus s, which combines to 1 minus s squared. So a good candidate would be this value. Now apply the first rule at node 8 itself, where r is equal to -1 and s equal to 0. Substituting gives a equal to 1 over 2. That gives the final shape function, n8, which is 1 over 2 times 1 minus r times 1 minus s squared. This satisfies both rules. It equals 1 at node 8 and 0 at all the other nodes. Now let's see how node 8 affects the other shape functions. At node 8 position, which is r equal to -1 and s is 0, if we check the old formulas, both n1 and n4 take the value of 1/2 instead of 0. That means node 8 would still be influenced by nodes 1 and 4, which violates the rule. But at node 8, only n8 should be equal to 1, and all the other shape functions must vanish. So just like before, we fix this by subtracting half of n8 from both n1 and n4, as you can see here. Now at node 8, both n1 and n4 correctly drop to 0, while n8 is equal to 1. This ensures that the left edge interpolation is also quadratic, just like the other 3 edges. Here we have the complete set of shape functions for the 8-node quadrilateral element. As you can see, nodes 1 through 4 are based on the original bilinear form, but each of them is corrected by subtracting contributions from the mid-side nodes, as you can see here. Nodes 5 through 8 are the mid-side functions, and each one has the form of a quadratic term along its edge and a linear term in the perpendicular direction. With these 8 functions, every edge of the element is represented by quadratic interpolation, which makes this the standard second-order quadrilateral. This element is widely used in finite element analysis because it balances accuracy with computational efficiency. It captures curved boundaries much better than the 4-node bilinear element, but without the extra complexity of the full 9-node case. Now let's move on to the 9-node element, the complete quadratic quadrilateral. We start with the 8-node element, which already had mid-side nodes along each edge. To take it one step further, we add a 9th node right at the center of the element. On the left, you can see the physical element in Cartesian coordinates, and on the right, the mapped element in natural coordinates. Notice how the numbering still follows the counterclockwise order, with the center node labeled as node 9. This extra node gives the element full quadratic completeness. That means its interpolation space includes all constant terms, all linear terms, and all quadratic terms, including the cross term Rs. In practice, this makes the 9-node quadrilateral very accurate for representing curved boundaries and for capturing complex stress or displacement fields inside the element. Now let's find the shape functions for node 9, the center node. According to the rules, n9 must be 0 at all the other nodes, that is nodes 1 through 8. So the function has to vanish at the boundaries of the element. That means n9 must include quadratic terms in both directions, something like this: 1 minus r squared times 1 minus s squared. This automatically ensures that the value is 0 wherever r and s are equal to plus and minus 1, which corresponds to the edges of the element. Next, we apply the first rule. At node 9 itself, where r is equal to 0 and s equal to 0, the shape function must be equal to 1. Substituting these values in gives us the constant a equal to 1. So finally the shape function for the central node is n9, which is equal to 1 minus r squared times 1 minus s squared. This makes node 9 unique because it activates only in the interior of the element, and it provides the full quadratic completeness. So how can we modify other shape functions? Nodes 5 through 8 are easy to modify because n is 1/2 at these nodes when r and s are equal to 0. So we just need to subtract half of n9 from n5 through n8. But modifying n1 to n4 would be challenging. n1 for q8, if you remember, had a formula like this. So if I just substitute n5 and n8 for q8 from q8 element, I will have an expression like this. So this is n1 for 8 node element. At r and s equal to 0, if we find n1 for q8 element, the value would be minus 1/4. So we need to add 1/4 to make n1 0 at node 1. Since n9 is 1 at r and s equal to 0, so we add 1/4 times n9 to n1 to form it for q9 element. I can rewrite it in this format. These are the same, but just I have tried to show n5 and n8 for q9, so we can have a formula like this in which all of the n values, n5, n8, n9 and n1, are related to the element with 9 node. So you can compare these two expressions. They're exactly the same, and I have just tried to show n8 and n5 for q9 element. So similar to n1, now you can modify n2, n3 and n4 and get the formulas for them as shown here. Here you can see the full set of shape functions for a 9-node quadrilateral element. You can see how 1/4 of n9 is subtracted from n1 to n4, and half of n9 is subtracted from n5 to n8. And also n9 is quadratic in both r and s directions, as you can see here. This final slide summarizes how we can systematically construct the shape functions for quadrilateral elements with 4 to 9 nodes. We begin with the simplest case, the 4-node element numbered counterclockwise, giving us n1 through n4, as you can see in the slide. When we add node 5, located between nodes 1 and 2, half of n5 is subtracted from both n1 and n2. When node 6 is added, half of n6 is subtracted from n2 and n3. With node 7, half of n7 is subtracted from n3 and n4. And with node 8, half of n8 is subtracted from n1 and n4. Finally, when we introduce node 9 at the center of the element, 1/4 of n9 is subtracted from each of the corner nodes n1 through n4, while half of n9 is subtracted from each mid-side node n5 through n8. This completes the derivation of shape functions for quadrilateral elements with anywhere from 4 up to 9 nodes.